Good morning, and today we're going to be looking at the graph of the derived function. Now we know that the derivative of x to the power of n becomes an x to the power of n minus 1. What I'm showing you there is that the power becomes 1 less than the original power. Okay, the power lowers by 1 as we know, so the derivative of a cubic function where x cubed is the highest power of x would be a quadratic. The x cubed would become an x squared. Obviously dependent on coefficients and so on. We haven't differentiated properly here. I'm just showing you that the power of an x cubed when differentiated becomes an x squared. Okay, so the name of a function or an equation is taken from the highest power. So this would be a cubic function, wouldn't it? Because it's an x cubed, it's the highest power. But when we differentiate that, then the cube is going to become an x squared. 6x squared. That's going to become an x. That's just going to become a constant and the number 9 disappears. So when you start with a cubic function and you differentiate that, it becomes a quadratic. Because the highest power of your differentiated function is now an x squared. If you have a quadratic to begin with, we would say that's a quadratic because the highest power is an x squared. Then we differentiate that and we have 2x plus 2. And we would say that the equation of the derivative now is a linear function, like a straight line. Okay, so if you've got a cubic to begin with, when you differentiate it, it becomes a quadratic. When you've got a quadratic to begin with, when you differentiate it, becomes a linear function, which is a straight line. So let's look at this graphically. Okay, when drawing a derived graph, all the stationary points of the original curve become roots, which means they lie on the x-axis of the graph of the derivative. Where the curve is decreasing, the value of the derivative is negative. Just remember what that means. Where the graph is going down the way, that would mean that the gradient would be negative, and the f dashed of x or dy by dx is going to be less than 0 then. When the gradient's negative, f dashed of x is negative. So when the curve is decreasing, not just the gradient becoming negative, but the derivative is negative. Okay, so the graph of the derivative will lie below the x-axis and it will take on negative values. Wherever the curve is increasing, the value of the derivative is positive, and that means that the graph of the derivative will lie above the x-axis and it will become positive values. So here we have some standard functions. So here we have a quadratic. Okay, and as you can see here, we have our turning point here. Okay, so what we do is you draw the graph of the derivative underneath the original function. And where we have the turning point on the original graph, you make that lie on the x-axis of the derivative, of the graph of the derivative. Okay, because we know that for a turning point, f dashed of x is equal to 0. This is the graph of f dashed of x, so we need to make it equal to 0 on the x-axis. Now this point here is showing you that the graph is going down the way. So if the graph is decreasing, we know that dy by dx or f dashed of x is a negative value. So we have to show that under here. By making it underneath the x-axis, it has to have negative y values. It has to be negative. And when the graph is increasing, which is what we have here, then the graph of dy by dx is going to be positive for dy by dx. All of the y values have to be positive, so it has to be above. So the turning point goes on the x-axis. If the graph is decreasing, this is the graph of the derivative. It has to be below the x-axis. If the graph is increasing, then this point of the graph has to be above the x-axis. Okay, and as you can see here, a quadratic has turned into a linear when you've differentiated it. So here we have a cubic. Okay, so here we have the turning point. So draw your graph of your derivative underneath and line up your turning points. Now at the turning points, at stationary points, f dashed of x is equal to 0. So we have to put these points on the x-axis of the new graph. So see how they line right up and they're now on the x-axis. So those turning points there go right down onto the x-axis of your derivative. Here we have a graph that is increasing. So that means that dy by dx would be greater than 0. So it just has to be above the x-axis here. Has to be positive. Here we can see the graph is between here and here. It's going down the way. It's decreasing. So that means that between here and here, it has to be below the x-axis, negative. And here we have a graph that is increasing. And we have to have a graph here for the derivative, which is above the x-axis, which is above and positive. Okay? And we can see here that a cubic function, as we showed earlier, would become a quadratic when we differentiate. So the cubic shows the graph of a quadratic when it's the graph of the derivative. Okay, here we have a quartic. Now a quartic is an x to the power of 4. Okay, so a quartic is an x to the power of 4. So here are all of our turning points here. We bring all of them down and make them go on the x-axis. That's the first thing you do. Wherever it turns, it goes on the x-axis. There. Okay. Here we have a graph that is increasing, which means it has to be above. So to the left of this turning point, it's increasing. So to the left of this, now root, it is above, positive. From this turning point to this turning point, we have a decreasing function. So we have to have it going below, negative. Here, from here to here, we are increasing again. So we have to have it above, which is positive. And to the right of this one, we have a decreasing function again. So here we have to have it below, which is negative. Okay, so it turns there and it goes on the x-axis there. If it's going down the way there, it means it has to be below. If it's going up the way there, it has to be above. Turning point on the x-axis, increasing above, decreasing below, increasing above. Turning point on the x-axis, on the x-axis. Now if these points are marked on, we make sure that the numbers are marked on there to show that they turn up there and they cross the x-axis at the same points below. That's increasing, means above. Decreasing, between here and here, means below. Increasing, above. And decreasing, below. Now if we have it below between 2 points, we have to have it obviously turn to get back to the root again. Okay? Now here we have a function that's given as x squared minus 4x plus 6. We know that dy by dx equals 2x minus 4. So here we have the original graph, the quadratic, and then the graph of the linear function would be shown there. Okay, now we've done this in a different way from the way you would get asked in the exam, because this is just demonstrating that here we have the graph of the quadratic. That's the turning point. That's where it is on the x-axis for the graph of the derivative. There it's going down the way, there it's below, there it's going up the way, and there it is above. Okay. Okay, so going back to this here, this is the way we're going to be drawing the graphs of these equations. You draw the graph below, the original graph. Any numbers marked on here would be marked below and there as well. If I told you that was turning at 2 and 5, you would mark the 2 and the 5 there. If I told you that was turning at, but whichever point, you would mark the points on the graph there. You won't be given the actual equation the way you are here. To find dy by dx, you'll just be given the graph and underneath it asked to draw the graph of the derivative. Okay, so we're going to look at exercise 6p and we'll try questions 1 to 8 and ask for help if you're unsure. Take care and good luck.